Hello, I'm Olga Savchuk, and I'm with IN Plus Center for Innovation, Technology and Policy Research at Instituto Superior Técnico in Portugal. Today, I will talk about the value of feature engineering and selection to improve energy demand forecasting in buildings. I would like to start by thanking Dr. Pablo Duenas, Derek Wisma, Joshua Rains, Steve Lanu, and Siobhan Carr for their expert advice. Also to Julie Newman, Stuart Eiler, and Dr. Ludovica Ilari for providing the data. Finally, to Portuguese Foundation for Science and Technology and to Inner Energy for financial support. Climate change crisis urges actionable solutions to reduce the emissions. Meanwhile, building operation generates nearly 30% of global emissions. Forecasting of energy demand enables more efficient operation while meeting the comfort level of the people inside. Furthermore, forecasting is instrumental for planning flexibility services and is helpful for enhanced maintenance. To forecast the demand, we need accessible, high-quality data, which is rarely available. That is why alternative data sources can be beneficial in capturing the patterns important for the prediction. Some demand patterns can be very well captured by physical models. However, the buildings with more stochastic and evolving behaviors will require increasingly complex approaches. Black box models are suitable for such complex patterns. However, they lack interpretability and oversight. Engineering and selection of input features for black box models enhance interpretability by clarifying which inputs are more valuable for an accurate forecast. Knowing which features are important can inform better data collection and retention procedures. However, there are also challenges. While some features are significant predictors for one building, it does not follow that the same features would benefit another building. Furthermore, there are diverse engineering and selection methods, and there is a lack of coherent methodology to make sense of them. Finally, comparative studies are lacking where the demand of multiple buildings in the same locations would be examined. This leads to three major questions. Which features have been used for demand forecasting, which features improve the prediction the most, and which feature engineering methods add the most value. To answer these questions, we analyzed recent peer-reviewed publications on electricity forecasting with black box models. Based on these results, we formulated a comparative study of demand forecasting in buildings with different function. Finally, we examined the contribution of different feature engineering methods to forecasting accuracy. We reviewed 100 published articles on prediction of electricity, cooling, and heating demands. We collected the input features and aggregated them by type. The results of electricity demand are presented on the right, where each column represents a type of feature. For instance, weather type contains solar radiation, wind speed, precipitation, and so on. Each row represents an article, and the number is the count of features within a specific type. The results show that the number of features used to predict electricity demand ranges from 1 to 47. Up to 6 different types were used within one article. Top most used feature types are time, weather, and previous electricity demand. Meanwhile, uniquely used features types including occupancy, grid features, and heating demand. Out of 118 MIT campus buildings, we selected 19, comprising 29 electricity demand zones. We selected 19 based on their overlap with Wi-Fi login count data. This limited the time frame to 8 months in 2016. We also considered weather features from 2 on-campus measuring stations. We then preprocessed the data. We applied 4 feature engineering techniques based on domain knowledge, statistical, frequency, and deep learning transformations. We chose filter method to select the features. We used artificial neural network with 2 hidden layers for one time-step ahead forecast. We formulated 3 cases. A benchmark case based on the electricity demand of the last hour. We call it lag demand. Second case included weather, time, and occupancy features, as well as their engineered transformations. And finally, the third case comprised the two above. We considered 4 different building use types: office, residence, laboratory, and sport facility. In the following slides, we'll see the electricity demand, occupancy, and weather patterns for the same week in April of 2016. The figure displays electricity demand patterns for the same week grouped by building use type. It is clear that there is a diversity of patterns in terms of periodicity and amplitude. Furthermore, analyzing the whole data shows that the buildings also vary in their stationarity. This figure displays Wi-Fi login counts per building, which shows similar diversity. 2 weather stations measure 10 common features, and only one measures solar radiation. The advantage of considering the 2 sources is the complementing of missing readings and measurement errors. All buildings were anonymized by assigning code names. Here's the forecasting performance of the 3 cases for office buildings. The results are expressed as coefficient of variation of root mean squared error, where purple marks the benchmark case, red all features but lagged demand, and peach all features together. Except for one case, all the buildings benefited from diversifying the features. Some buildings benefited the most. Except for the 3 highlighted buildings, addition of lagged demand has mildly improved the forecast. Compared to office buildings, residence, laboratory, and sport type buildings have less regular use pattern due to their occupancy. In case of the laboratories, the experiments can be energy intensive and sometimes continue past regular working hours. Such complexity of demand pattern may explain the modest improvement in errors after adding further features. When we look at all building cases, more than half had performance error less than 15%. Over a third had error between 15 and 30%, which is frequently used as the maximum acceptable error for energy demand forecasting. Yet 3 cases had unacceptably high errors. We also analyzed the frequency of occurrence of feature types. There are 2 bars per building. The top bar is all features except the lagged demand, and the bottom bar are all features together. Colors indicate the feature types. We observed that regardless of building occupancy type, most buildings are predicted using the full range of proposed feature types: time, weather, electricity, and occupancy. After added lagged demand, 12 cases used fewer features, 14 cases used more features, and 3 cases used the same number of features. When fewer feature types are used, it is often weather that is reduced in number. This may mean that the added demand features are more relevant to the prediction. In some cases, electricity features are only ones that are kept, and everything else is dropped, which means that previous hour demand have more importance than the dropped features. Yet in some cases, for electricity-only features, the building is predicted by employing the range of feature types, which leads to mild improvement in the error. For the buildings where the feature types ratio remained unchanged, the error has improved, which can be explained by the fact that the actual feature composition has changed. Overall, the change in feature type composition is not uniform across building occupancy types. Finally, the most employed feature types within both sets are almost equally weather and electricity demand, which being used slightly more than twice as the occupancy. Meanwhile, time features appear to be used slightly less. This can be explained by having much fewer time features proposed relatively to the other feature types. Similarly, we analyzed the frequency of use by feature engineering method. In the majority of cases, 2 or 3 engineering types are employed. The number of selected features range between 4 and 29, with strong preference for diversifying engineering types. We observed that statistical features are used the most, followed by autoencoded ones, and then non-transformed ones. Frequency-based features have not been selected for any of the buildings. With addition of lagged demand, more non-transformed features appear, without a reduction of number of engineered features. Yet it does not mean that those are the same features used as before. Finally, lagged demand improves the error in the majority of cases. Yet, even after adding lagged demand, the engineered features have a significant contribution to maintaining the low error measure. Our study has explored the contributions of raw and engineered features for electricity demand forecasting. Focusing on the case of multiple buildings with diverse occupancy types, yet in the same location, provided the basis for comparison of features by their nature and transformations applied. We concluded that lagged demand is a beneficial and necessary feature for electricity demand forecasting, regardless of the building use type. If fewer features are used, it is the weather features that are dropped compared to time, historic demand, and occupancy. Strong preference to diversify the nature of features, both in terms of feature type and type of engineering procedures applied, has been observed. If you would like to continue the conversation on this topic, feel free to reach me here.